Okay, so this question is looking at alternative energies, in particular hydrogen, oxygen fuel cells. And the first one says given advantage of using a hydrogen oxygen fuel cell rather than a chemical cell to power a vehicle. And so hydrogen oxygen fuel cells, as long as they are supplied with fuel, they'll just continue to produce a voltage. So we can make that one of the advantages. So we can say as long as they are supplied with the fuel, so the fuel in this case is the hydrogen and oxygen, as long as they're supplied with the fuel, they will continue to produce a voltage. A normal cell, an alternative cell, and a normal cell will actually, the voltage will decrease over time. Complete the half equation. This is a tricky one, tough question. So if we just approach it in a simple way, there's two oxygens here, and I've only got one oxygen here. So to make this work initially, it looks like I'm going to need a big 2 in front of that. But what that will do is give me 4 lots of hydrogen required. So if I come back over here and therefore put a 4 in front of the H+, because I've got 4 positive hydrogen ions, I'm also going to need 4 negative electrons in order to balance out the charge on that side of the equation. Marks wise, you get 1 mark if you put down the electrons here, and you get another mark if all the balancing is correct. Okay, next one is calculate the volume of oxygen. So to calculate a volume, what we have to do first of all is convert the mass into moles. We need to be working in moles. So step number 1 is we're going to work out the moles of oxygen. And according to our equation over here, the moles of oxygen is the mass divided by the MR. So in here, I'm going to put mass divided by MR. So the mass is 48. The MR, now be careful because oxygen is O2, and therefore that's going to be 2 lots of that is 32. So let's put that into my calculator. So I've got 48 divided by 32 is 1.5 moles. The second step now is I'm going to convert this number of moles into a volume, and to do that I'm going to use this triangle. So the volume is moles times 24. So let's put that here to help me. So volume is the number of moles times by 24. So the number of moles we've just worked out is 1.5. Times that by 24. So times that by 24, and that's giving me an answer of 36, and that's going to be the decimeters cubed. Okay, the next question is a 6 marker, and there's a lot of information here that we need to use to help us. So we've got this equation that's a equilibrium equation, so it's reversible. The reaction is endothermic. So what I've done, just to help myself, I've rewritten this out with a bit of space. And because it's telling me here that the forward reaction is endothermic, I've actually written that on here. So the forward reaction is endo, and that means it's going to take energy in and make the surroundings cooler. It also means that going backwards, the opposite way, is going to be exothermic. Exothermic release heat, so that would make the reaction, the surroundings feel hotter. It tells me the conditions are a nickel catalyst and a temperature of 220 degrees. Explain, in terms of their effect on attainment of equilibrium and the equilibrium yield of hydrogen, why this reaction is carried out at using a catalyst and at 220 degrees rather than without a catalyst and at a lower temperature. Okay, so I need to talk to them about attainment, so that's part 1, and equilibrium, and why a catalyst is better and why this 220, which is a higher temperature, is also a better condition for this reaction. So let's split my response up into different parts. Let's deal with the catalyst first, just because it's listed here first. And the things we need to remember about a catalyst are that catalysts increase the rate of attainment of the equilibrium. That means they set the equilibrium up in a shorter time. They do that by increasing the rate of the forward and backward reaction by the same amount. They're able to do that by lowering the activation energy, and that happens because they provide an alternative reaction pathway, and the catalyst has no effect on the equilibrium position, so it doesn't make it move to the right or to the left. All it does is increase the attainment, the setting up of the equilibrium. So they're the bullet points for a catalyst. If I now scroll down, and we're going to come to temperature. Okay, so if we look at the equilibrium yield with temperature, so at a higher temperature, so if we're going to use this 220 rather than a lower temperature, at a higher temperature, if we think about Le Chatelier's principle, it says that if we go for a high temperature, it will try and lower the temperature. How's it going to lower the temperature? Well, let's just come back up to our equation. If I want to lower the temperature, I want to make it cooler. Therefore, I'm going to move towards the right, and I'm doing that because the right is endothermic. So let's come back to our answer. So Le Chatelier says it's going to try and lower the temperature. To do that, the equilibrium will shift to the right. That's because it's endothermic in that direction, and because it's going in the right, that's where the hydrogen is, and therefore I'm going to get more hydrogen produced. So we've got more hydrogen is being produced. Right, the second part of this answer needs to look at attainment. That's setting up the equilibrium. So when we have a high temperature, the particles move more, they've got more kinetic energy. And if they move more, they're giving it more chance of successful collisions. And these collisions will also have energy greater than the activation energy. More of them have energy greater than the activation energy. And that means that the equilibrium is set up in a shorter time. So it's set up more quickly. If you count the bullet points, there are 15 there. So what we've done again is split it up. So if you've got over 13, you get 6 marks, over 11 is 5, and so on and so on and so on as you go down. So you can award yourself a number of marks based on how many of those bullet points you have got.